recording. Okay, we're live. So we are going to finish off the 1.4 lesson today. We did this part one yesterday. So we are right here on whatever page number that is. Page 29. Can everybody turn to page 29? And we are going to, oops. That's what I want. There we go. Okay, so example 4. Sketch f of x equals x squared minus 1. Okay, so using my grade 11 skills, I'm going to write this. I'm going to do this in a very light color here. Let's see. What do I got? Do I have a lighter blue than this? Or how about a lighter green? I don't know. What is that? That's like a. It's supposed to be a pencil crayon or something. That's why it looks like that. Okay. All right. Oh, we'll do it in this light green. Okay. So in my light green, I'm going to make f of x equals x squared minus 1. So x squared minus 1 is a parabola that's been shifted down 1. 1, 2, 1, 2, 3, 4. And then by symmetry, there it is. There we go. Will the inverse of that be a function? No. And the reason why is because it fails. Oops. If. I meant to say it. It fails the horizontal line test. Look back to yesterday's notes if you need a refresher on what I mean by that. But basically, you learned in grade 10 that a vertical line test will tell you if you have a function. But if I'm going to inverse something, that's going to rotate it, or it's going to reflect it across the line y equals x. It's going to reflect along this line. This line becomes the mirror. So you can probably tell by looking at it that's going to actually flip its direction, and then it would fail the vertical line test after that. So the horizontal line test tells us that it will fail the vertical line test once I reflect it in that red line. Okay, so now use the graph of f of x to sketch the graph of the inverse. So, okay, I'm going to go back and put the original graph in, but this time I'm going to put it as a dotted line. So here, 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 and 1, 2, 1, 2, 3, 4 here. 1, 2, 1, 2, 3, 4 here. So I'm going to put it as a dotted line. So it's kind of not in my way so much. You know what I'm saying? There we go. And you know what? While I'm at it, I'm actually going to put in, again as a dotted line, the line I'm about to reflect in. And I just really drew that poorly. So I'm going to try it again. Let's try that again. It goes through 1, 1. It goes through 2, 2. It goes through 3, 3, etc. There. That's the line y equals x. This is the line y equals f of x. And now I would like to graph y equals f to the, sorry, I'm having all kinds of technical issues with my pen today. That. So that's what I'm going to graph in black here. So the first thing I'm going to do is maybe talk about the invariant points. So what are the invariant points? Well, let's see. Oh, wait a minute. I was supposed to actually graph that up here. Sorry. I just realized that. Okay, so I'm going to graph it up here. Okay, so let me go back and put that on there. That's f of x. And this is y equals x. Okay, so up here, I'm sorry, I was looking at the wrong spot. Okay, so the invariant points. Remember that when you're on a reflective surface, you don't change your position when you reflect. So that is going to be a point, and this is going to be a point. Other than that, I just have to switch my x and y. So remember that this point here, this vertex, is the point 0, negative 1. So negative 1, 0 becomes the new point in the reflection. I know parabolas are symmetrical, so there's going to be this point here that I just drew on the reflection line would have a point in symmetry up there, say. And then just pick another point. Here's another point. How about this one? This point up here, right now it's the point 2, 3. That means that 3, 2 will be a point. And I think I've got this from here. And again, by symmetry, I know that there's a point down here. There we go, something like that. I'm drawing really fast. It'll give you a sec to catch up to me. Finish my morning coffee. Anybody carry a makeup mirror? Okay, if you carried a makeup mirror, what you could do, it has to be, it can't be a round one. It has to have an edge. It has to be square. At least one edge of the mirror is a straight line, a square, a rectangle, whatever. If you take that makeup mirror and you like set the edge of it along the dotted line, along this line, the green and black parabolas here will look the same. They will reflect each other. I don't know if my diagram's perfect. It's probably not. But you get the idea. Maybe just to show you what we're actually doing. Here's what this diagram should look like if I did it nice and accurately. Go to Desmos. And so the first graph is, come on Desmos. The first graph is y equals x squared minus 1. The second graph, I just switch x and y. So x equals y squared minus 1. So there. That is what I was trying to accomplish in my diagram. Oh, and I did draw the line, the reflection line. So the reflection line was, here, I'll even color them the same. Let's see. This one was in green, right? So this one was in green. And I did this one in black, right? So that one was in black. And I did the reflection line, y equals x, I did as a dotted red line. So let's make that red and make it dotted. I said red and make that dotted. There. That was what I was going for. Let's see. How good was it? I made this a little too bulgy at the bottom, I think. Oh well. You get the idea. Okay. So my lack of graphing skills aside, that's what we should have. Okay. How can we restrict the domain so that the inverse is a function? So y equals f prime of x, oops, can only be a function if it passes the vertical line test. True? If the vertical line hits it twice, it's not a function, because then every x doesn't have a unique y. Every input doesn't have its own output. Were you listening yesterday when I told the toaster story? Toasters are functions. Every time you put in bread, out comes toast. If you had a machine that you put in bread and out comes a Pop-Tart, you put in a bread, out comes a bagel, you put in bread, out comes an issue of Life magazine. Something's desperately wrong and it's not a toaster, okay? So, going back, what could I do to the green function so that the black function would turn out to be, or to the black parabola would turn out to only be one-sided, so it doesn't have two sides. So what I can do is I can say that I can restrict, let me turn on the pen, I can restrict the domain of f of x to be x is greater than or equal to 0. So instead of that entire dotted parabola, the green one is now only this arm. Which means that its reflection in that red line, its inverse, would only be this black arm from here. Come on, black pen. There we go. From here to here. And of course, it would also go through here, wouldn't it? And this is y equals the inverse. Okay? It's only one arm, so it's totally going to pass the vertical line test now. Is it possible to give another answer for part C? The answer is yes. Yes. I could have restricted, f of x to x is less than or equal to 0. And then my graph, make yourself a little sketch, then my original parabola would have gone this way, and my reflected parabola through the line y equals x, my reflected parabola would have gone this way. Actually, I just drew that badly. Let me try that again. Blah, 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 blah. Let's try that again. Give me a mulligan on that, would you? Because I forgot that the green parabola started down here. Started down here. This is the line of reflection. And my new parabola would have started from, let's see, so the point 0, 1, or 0, negative 1 would have reflected over to negative 1, 0, which is right here. I didn't draw this all that great either, but it's a bit better. There. So this green one is f of x, and this black one is f to the negative 1 of x. And then maybe I'll say it just in words here. So f primed of x is the other arm of the parabola. There we go. Okay, now let's do this algebraically. Write the equation of the inverse relationship. Okay, well, let's see. If the original equation was f of x equals x squared minus 1, and we did this yesterday, think of that as a y, and then the inverse happens when you switch x and y. So I'm not going to say that this thing's equal. I'm going to use an arrow or something. And this is my inverse operation now. So x is now equal to y squared minus 1 when you do the inversing of that equation. So now I have to rearrange it for y. So that's going to be y squared is equal to x plus 1. And then, do you remember when you square root both sides of an equation? Does everybody see that that's the next step, right? Because I'm isolating y. Remember when you square root both sides of an equation, you actually get two possible answers. When you first learned how to square root back in grade 8, you were only doing it to do Pythagoras, right? Remember, c squared equals a squared plus b squared. So say you had c squared equals 16. You'd just say, oh, so c is equal to 4. But that's actually not the entire case here. Looking at it algebraically, a number times itself is 16. There's two numbers that fit that description, 4 or negative 4. But in grade 8, the length of a side in a triangle is going to be negative 4. You'd never think that way. But we can think that way now, especially when we're talking about coordinate geometry, right? Numbers can have directions. You can go in a negative x direction or a negative y direction. So this equation, when I square root it, does have a plus or minus on it. And that makes total sense with what we just drew, right? Either it's the positive arm, which I'm trying to show you over here. It's the positive arm, or it's the negative arm that is the function. Okay? Okay. Now, one last thing in this chapter is proving functions are inverses of each other. If I have two pieces of algebra, how can I tell if they're inverses of each other? If I had two graphs, it's easy. I just look at the graph and go, oh, if I drew the line y equals x, is that the mirror that those two graphs reflect over? And if the answer is yes, oh, there you go, they're inverses. But if you're just looking at their algebra, check those two out. Do those two look like inverses of each other? You probably don't have enough experience with inverses to look at it and tell. So there must be a method that I can use to figure that out. What can I do for you?
Mirrors are fun.
Mirrors are fun.
I'm doing sine law again today.
Oh, okay.
Yeah.
I did introduce cosine law, but I didn't go to angles. I just did sides.
I'm not going there.
Okay. All right. I can slow down tomorrow then. I am boring the double dipper something terrible though.
Yeah, you know what?
Yeah.
That's okay.
Yeah. Okay. All right. Moving along. Sorry about that. I had to have a conversation with a colleague there. Show that those two things are inverses. So basically, what I'm going to do is I'm going to find f of g of x. Ooh, do we remember what that means? You were supposed to see that back in grade 10 when you were doing functions. It means take the g function, which is this thing, and put it in to the variable of the x function. So that's going to equal 3, and then instead of x, put in what the other function is. And now let's simplify that. Those 3's cancel. And I get just x. And this is actually the rule. If f of g of x equals x, then f of x and g of x are inverses. And I don't know why I put a space in inverse, like it's two words, are inverses of each other. And what that means is g of x is equal to the inverse of f of x. And no, I didn't misspell the word if. My spelling's not that bad. That means something in math. That means if and only if. But now that I wrote that, I'm kind of regretting it, because there actually is another way you could prove it. In fact, let's try it. I didn't leave myself a whole lot of room. Hopefully you were smarter and wrote smaller than me. What if we find g of f of x? What if we now go the other way? Let me use a different highlighter here. What if we take the f of x function and we plug it in to the x of the g of x function? So I'm going to do that. So g of f of x is, instead of x plus 5, it's 3x minus 5 plus 5 all over 3. Do you get what I just did? I basically just used this function, but I replaced the x with the entire f of x. So that's what we call g of f of x. You put one rule for x inside of the other. Again, if I like to think of functions like they're machines. You saw me compare a function to a toaster. Well, suppose that you have in your kitchen, you have your toaster and you have your microwave. What if we put the toaster inside the microwave? It both toasted and heated up at the same time. Now, I actually would not recommend you try that. Don't try that at home. I take no responsibility if you burn down your kitchen trying to put the toaster inside the microwave. But mathematically, you can totally do that. Right? If I have a rule that says, take the x numbers, times them by 3 and minus 5, then I have a rule that says, take the x numbers, add 5, and then take that answer and divide it by 3, I can put one rule inside the other. I can say, hey, I'll take the x numbers, times by 3 minus 5, and then I'll add 5 and divide by 3. Because you can do that in math. Not so much with kitchen appliances. So now the answer to that, can you see the algebra on this? It's quite beautiful. The bracket here doesn't really mean anything. So minus 5 plus 5 cancels, and you have 3x divided by 3. So maybe I should amend my if. I should say or g of f of x equals x. Then they are inverses of each other. All right, why don't you try one? Does g of f of x or does f of g of x equal x? So let's try f of g of x. Does f of g of x make x? So if I take f of x and I replace this x with x plus 4, what do I get? I might have to change the battery on this thing. Sorry, quick technical issue here. Okay, there we go. So I get x plus 4 minus 4, which is x. I didn't mean to put an equals after that. Therefore, f of x and g of x are inverses. Next, let's try finding f of g of x on this one. So I'm replacing this x with everything g of x is. So that's 8 times x minus 3 over 8 plus 3. So what's that going to be? Well, the 8's cancel, right? And I have x minus 3 plus 3, which is x. Therefore, f of x and g of x are inverses. And remember, there's another way you could say that. You could say g of x is equal to the actual symbol for the reciprocal of, or sorry, not the reciprocal, for the inverse of f of x. All right, one more. Let's show that those two are inverses. So f of g of x would be replace this x with 2x plus 2. And that's going to be 2x over 2, which is equal to x. Therefore, g of x is the inverse of f of x. And that's it, right? They didn't give you any more examples than that. Nope. So now it's the 1.4 worksheet, which I told you could start yesterday. Yesterday's lesson could get you 1 and 2 for sure. And now you can actually do the rest of them. You can do number 3. Actually, now that I think about it, though, number 4 is kind of a dumb question. I do enjoy playing with that formula, but that question is not asked very well. So you know what? We're just going to do 1 to 3. So 1.4 worksheet 1 to 3 is basically your homework for this. And that's our last new lesson. So that should be not a whole lot of homework for tonight. Let me stop my video here.